Okay, okay. Thanks, Arvid, for inviting me to share with your section on this topic, sources of variation analysis with multivariate charts and GLM, general linear modeling. Um, I'm Chief Technology Officer and co-founder at Sigma Excel. We are a software company producing uh, an Excel add-in for statistical and graphical analysis. I have been an ASQ member since 1989, um, and I'll be attending the World Conference on the WCQI in May and giving a talk there on fraction of design space plots. So if you're going to be there, then you might want to consider coming to my session there. And let's see, anything else? Well, yeah, just so by way of background, I taught at Motorola University. I was never a Motorola employee, but I was a contractor to Motorola, independent consultant for many years in the applied statistics and Six Sigma quality area, um, and worked with a lot of different organizations in a lot of different industries, transactional and manufacturing, and did a lot of training, green belts, black belts, and I am a certified master black belt from Motorola University. Sorry, not ASQ, but anyways, I guess that's the background. And so today I'm here to share with you really how to improve your process by understanding your sources of variation. That's kind of the focus here. So I will introduce the general linear model for variance components. We'll talk about basic sources of variation within, between, over time. We'll look at a couple of graphical tools that are helpful in this situation where we have variance components, namely the multivariate chart and the three-way control chart I-MR-R, that's individual moving range or individual moving range standard deviation. We'll look at that. We'll look at then using the general linear model to analyze the within, between, and over time data. Then we'll shift gears and we'll use GLM to analyze destructive Gage R&R test data, shear test data. So once a wire bond is broken, it cannot be retested. So that's an application for nested Gage R&R. And then finally, we'll do a kind of a more advanced case study, which mixes everything. It has fixed factors, random factors, nested, crossed, and is unbalanced. So just kind of throw the whole kitchen sink together. And it's a nice little example from Douglas Montgomery's book, Design and Analysis of Experiments. And then we'll open it up to questions. And I have references. The PowerPoint is available on the Tennessee, the website. Arvid has made that available, as well with the data sets. And the references are here in the PowerPoint. So I'd like to start with kind of a graphical view of the kind of data that we're collecting that would be of interest for a sources of variation study. And so supposing we have temporal, week 1, week 2, week 3, and then within week 1, we have unit 1, unit 2 with unit 3, and then within each unit, we have multiple measurements. So we have within unit, between unit, and over time. Now, this is a general family of variation or kind of a way to tag the different sources of variation as a description. But this could, instead of time, this could be in a semiconductor manufacturing, this could be a batch number, batch 1, batch 2, batch 3, and this could be actually, yeah, this could be wafer 1, wafer 2, wafer 3 within a batch, and then this would be within wafer measurements. Or in a transactional process, you might have week 1, week 2, week 3, location 1, location 2, location 3, and then cycle time readings within each location. All right, so it's just a general framework And what you're interested in from an improvement point of view is, what is the dominant source of variation? Is it week to week? Is it unit to unit? Or is it within unit? Because depending on which of these holds the biggest source of variation is going to drive where you apply your improvement efforts and your implementation of statistical process control. And the tool that we will use to get actual percent summaries is the general linear model. So by breaking down the total variability into parts attributable to different random factors, it becomes possible to understand what sources of variability are contributing the most to overall variability. This then helps to prioritize improvement efforts for variation reduction and statistical process control. GLM can also be used to analyze Gage R&R study data and provides much greater flexibility than a classical analysis, which can lead to measurement system solutions that otherwise wouldn't be found. So for example, destructive nested Gage R&R, expanded Gage R&R that would have, in addition to operator and part, a test fixture, a location. And GLM can handle either fixed or random factors and interactions between these factors and unbalanced data. Complex formula details will not be discussed in this presentation. We will use Sigma Excel software to demonstrate, but anything that I'm demonstrating here can be done with other statistical software, including the R package, LME, linear mixed effects model in R. So if you're familiar with R, this package would allow you to do anything that I'm presenting today. GLM solves the variance components using ANOVA expected mean squares, but it can also be extended using restricted maximum likelihood. And like I said, I'm not going to get into the details, but it's the restricted maximum likelihood that provides confidence intervals for the variance components. Or if the design is unbalanced, restricted maximum likelihood is used instead of expected mean squares. And so its definition, a fixed factor includes data for all levels of interest. For example, there are only 2 test machines in a plant, so that would be a fixed factor. Whenever you're doing one-way, two-way, ANOVA, multiple regression, the factors are assumed to be fixed. A random factor, however, has levels that are randomly sampled from a larger number of possible levels, but interest is in all possible levels. So Gage R&R studies typically assume that part and operator are random factors. And a classical Gage R&R study is crossed. So here we have the picture where each operator can test each part. Nested Gage R&R, each operator tests its own separate parts because, as we discussed in a destructive Gage R&R, in a destructive Gage R&R, the part is destroyed, so that can't be passed on to another operator to do measurements on. So back to this diagram again, over time, unit to unit, or between unit. So within unit, down here, unit to unit, that is between, and temporal. And that's what we're going to look at. First, graphically. So to look at this graphically, the best tool is the Multi-Vari chart. So let me just quickly open up the Multi-Vari data and produce a Multi-Vari plot of the, I'll start with the within. So I have different data sets to highlight, and dominant within, dominant between, and dominant over time. So I'm going to do graphical tools. Multi-Vari charts, and my response is, my measurement is my response. Time is a discrete category, and I want, unit to be my group category X1 and time to be my X2. And then I'll produce the Multi-Vari chart And this chart just takes a few seconds to produce. The within unit is, you can actually look at the within unit, the within unit is the height of the bar. All right, that's the height of the bar. The unit to unit is this red line, and then the temporal is basically this is the time 1 average, the time 2 average, and the time 3 average. So you can see that week 1 to week 2 to week 3, the mean doesn't shift much. You can see visually that the unit to unit variation isn't really changing much. However, the tall line is highlighting the fact that in this example, the dominant source of variation is within unit. And now what I'll do now is we'll do the same, but with between. So we'll do the same analysis, and we'll go to the multi-vari chart, and we'll look at measurement, unit, time. And in Excel, it just takes a few seconds to produce the charts because they're pretty complicated charts. And so here you can see that again, week to week doesn't change much. The within unit vertical bar is not really that tall, but the unit to unit, the between unit, is the variation is quite large. So you can see the dominant within unit variation. And then lastly, we'll look at over time, and we'll do the multi-vari chart. And again, measurement, unit, time. So you can see week to week is now the dominant source of variation. Okay, so the temporal is the dominant source of variation. So just looking at this, depending on the nature, which of these is your dominant source of variation is going to help you to focus your efforts. In this case, what's changing from week to week. If it's between, what's changing from unit to unit. If it's within, you know, that becomes more of a repeatability issue. And what is it that is going on within unit that is contributing to the variability? So it just helps you in your troubleshooting if the goal is to reduce your variation or reduce your cycle time, whatever your goal is. Having a tool like this helps you to prioritize your efforts. Now that's the graphical. The other graphical tool that I wanted to mention is the individual moving range individual moving range I-MR-R, I-MR-S. And the reason we want to do this, I want to start with, I'm going to go to the between sheet, and I'm going to just do a classical X bar and R chart. So I want to motivate why the three-way chart is a good graphical tool to use when you have data structured like this. So if you were to just apply a regular if you were just to apply a regular control chart, and we'll treat the unit as a subgroup. So again, I'm looking at this data, creating a control chart, just a regular X bar and R chart, and what we see is that everything is out of control. But the range chart looks good. So you do we have a problem with assignable causes? Well, in this case, no. The problem is that the dominant source of variation is between, whereas we are using the within subgroup variation to compute the control limits. So the control limits are too tight. So what do we do about that? Well, we use the I-MR-R chart. So we go control charts, I-MR-R, it's also known as the three-way chart. And so measurement, unit, and run with that. And basically what this does is it treats the subgroup as an individual value, computes the mean, and plots the mean on an individual's chart. So I am individual moving range. This is a moving range. And then also the range chart from the X bar and R is shown as a third chart. So you can actually look at the different levels. But now you can, now there's not enough data points here to really conclude much, but I wanted to convey the concept. So, I wouldn't necessarily assume that this is a problem on the moving range. I'd want to collect more data. But the point is that what appeared to be a wildly out of control process, running the I-MR-R chart, you can see that it is a stable process, at least to the best of our ability to work with the data that we have. Now, so those are the two graphical tools I wanted to mention. Now, the thing about sources of variation is that I gave you three rather distinct examples, but you might have situations that are more kind of in between. Maybe there's contribution from between and temporal, and we'd like to know, we'd like to get a better measure of those contributors or bucket sizes. And to do that, I'm going to go back to the within sheet, and I'm going to go to statistical tools, general linear model. In the general linear model, it's very similar to regression, but the difference is that you have the ability to deal with these random factors. All right, and continuous factors, we call them covariates. In the categorical, we have two. You can either have fixed categorical or random categorical. So we'll start with the measurement as the response. And the two random factors will be unit and time. And I need to add nesting here because unit is nested within time. All right, so unit is nested, the parentheses denotes nested in, so unit nested in time. And now I'll just go ahead and run that. And I can create a model. In this case, I'm going to just go with the default terms. Actually, let me put time. I want to put time on the top. So let me do it first, time first, and then unit, so we can be consistent with the picture. And so when I do that, I see here that my error term, which is my within, contributes to 100% of the variation. And the time and the unit within time are 0. If you can have negative variance components, but we just set those to 0 when you have a negative variance component. So you can see that the within bucket here is contributing to 100% of the total variation. So it's definitely the dominant source of variation. This is also, well, this is the error term. And also we can see that time and unit nested in time are statistically insignificant. So you have the 0% contribution, and you have the fact that they don't show up at all in terms of statistical significance. Then standard deviation are provided just for convenience, and this will become more interesting when we get into using this for measurement systems. But I'll leave that for now. I'm mainly focused on variance components. And then we can actually repeat this. Maybe just to save some time, I'll show you on PowerPoint. So I have, if I rerun the analysis for the between, you can see the unit nested in time contributes to 98.3%, and the within is 1.7%. And the unit is significant. And then if we go to the over time, you can see that temporal is contributing to 98.5%, and the between is 0.6%. And they're both statistically significant. So as I said, you can use this now as a helpful guide to focus on the right things in terms of variation reduction. Another point I wanted to mention is that in addition to the actual variance components, the software gives you confidence intervals. Okay, and that's using the what's known as restricted maximum likelihood to get those. Okay, so that's basically all I want to do for example 1. Now, example 2 gets perhaps a little more interesting, is a destructive Gage R&R study. And in this example, we have shear test for a resistance spot welding process. Now, a destructive test has its challenges in terms of doing measurement systems analysis, and that is once the part is measured, it cannot be remeasured. So what, in this particular study, they did a DOE, but where they varied preheat temperature, preheat current, welding temperature, and welding current, and did a 4-factor, 8-run fractional factorial design to create quote-unquote parts. And they replicated this 6 times for each run for a total of 48 welds. So basically what that did was that gave them a range of tensile strength values. So you have tensile strength values that shared common conditions of preheat temperature, current, welding temperature, and welding current. And then by doing so, you could actually, it's similar to getting a regular Gage R&R, even though you are destroying the part because they're homogeneous. So within each group, you have homogeneity, and you're able to utilize that for your nested Gage R&R study. And 2 shear test machines were used, and each machine tested 8 parts with 3 replicates. The shear test machines are the operator, and they were treated as a random factor. You need to, in order to get variance components, the easiest way to do that is to treat it as a random factor. But this is what they did in the study, so we're just going ahead with what they did in the study. Tensile strength in newtons is the measurement that will be used. So we have tensile shear strength, the data, and we're just going to go straight in and analyze that just as we did the previous using general linear model. By the way, we do not have a nested Gage R&R tool. We use a GLM, and then we have a template that can copy. You can copy and paste the variance components in order to get your Gage R&R metrics, and I'll demonstrate that. So, because the hard part is getting those variance components. So again, tensile strength is the response. So operator and part are random factors, and we have part nested within operator. And then I'll go ahead and we'll pick operator and part nested within operator as the model. So here we see that operator is not significant. Part nested within operator is significant. And in the variance components, operator has a 0% contribution to the total, whereas part nested with an operator has 91%, or sorry, 91% of the total. The error is 8.95%. So it actually doesn't seem that large, but when you convert this to standard deviations, you can see that the error, which is the repeatability, is in fact 29.9%. So that's actually just acceptable. Just it's a marginal measurement system. Now, what I'm going to do to convert these into the more standard Gage R&R notation, we have a template. So under measurement systems, we go to templates, and we'll go to, basically we'll just populate this template to convert variance components into traditional Gage R&R. So I'll just copy and paste the three variance components into the template, and then this gives us your percentage of total variation. So that was what I said earlier, the repeatability, because there is no reproducibility, so 29.9%. So it's a marginal measurement system. So, but the thing is that you wouldn't have been able to just take this and just apply regular Gage R&R methods because of the nesting, and so you have to have the proper tool to get the variance components, and then you can quickly convert those into Gage R&R metrics. So that's the second example. And then the third example I have comes from Montgomery's book, and it's assembly time nested factorial. This is from Montgomery's book, example 14.2, and it's been modified. It is a balanced example in the book, and I made it an unbalanced example. So what it is, it's a process is a hand insertion of electronic components on printed circuit boards, and the goal of the study is to improve the speed of the assembly operation. The design includes 3 assembly fixtures and 2 workplace layouts. Operators are required to perform the assembly. In the book, 4 operators are randomly selected for each fixture layout combination. However, here we will use 4 operators for layout 1 and 3 for layout 2, making it an unbalanced design. The operators chosen for layout 1 are different individuals from those chosen for layout 2, so operators are nested within layout. Because there are only 3 fixtures and 2 layouts, these are fixed factors, but the operators are random. So this is a mixed model. The treatment combinations in this design are run in random order, but the worksheet is shown in standard order. 2 replicates are obtained, and the assembly times are measured in seconds. So it's actually a pretty complicated design, and we're not going to get into the mathematical details. The software takes care of that, but we do want to understand how to interpret the results. So let me go back to the data, to the assembly time data, and then we'll run
John, are you still there? Are you frozen? Can anybody hear me?
I hear you already.
Okay, looks like he's frozen at the moment. He's unshared and coming back, hopefully.
Okay, we're back on?
Yes,
Okay.
You're back up. Can you share again?
Oh, okay, sorry, was I cut off?
Yeah, we lost your sharing when we lost you. So if you can share again.
Oh, I'm sorry. Oh, did I unshare?
No, you got frozen for something. You had some kind of internet glitch.
Okay, so we got an internet. Okay, share screen. All right. So okay, so I'm um now were you able to hear me?
No, you cut out on us when you were getting ready to start that one right there, and you were in the data set getting ready to
Okay,
enter it in.
okay, good. Okay, so we really didn't. So did you see me set this up?
No.
Let me, you know what, that's fine. Let me walk. Okay, I'm going to walk it through. No, I'm going to take it from the top. All right, so this is the data set for, excuse me, the assembly time from the Montgomery book, example 14.2, the unbalanced data. And so I'm going to go to general linear model, and the response is time, assembly time. We have two fixed factors, fixture and layout. And operator is the random factor. And we have operator nested within layout. Remember I said that different operators for each pretty complicated model. Fortunately, the software resolving a mixed model is not straightforward. But we're going to be, and I also want to do main effects plots because that will allow me to look at some of these fixed factors. So we kind of, it's a hybrid. We're interested in traditional ANOVA type analysis, and we're interested in variance components. All right, so we're in this case, it's a mixed model, so we want to kind of take a hybrid approach to analyzing the data to see what we need to do to improve this process. All right, so in the next slide, what I'm going to do is I'm going to ask for main effects plus.
I think he froze again. If you hear me, something on his end is freezing up, I think, or it's on my end. I'm not sure. Can anybody hear me?
Yes, I hear you.
Okay, so it's on his end again. Unfortunately, this happens sometimes. John, can you hear me? John, we lost you again. Are you back?
Oh gosh, did you lose
Yeah, we
me
lost
again?
you again. We lost you again.
Hello.
Yes, we lost you again. Can you hear us?
Okay. Yeah. How far? How much did? How far did we? How much did you hear from what I said?
You were getting ready to, I think, run the model. So can you share that again and run that model?
Okay. All right. Yeah, I'll do that again. I hope uh, that's okay. Try that from the top. So let's see. Okay, so back. Okay, so I'm back to the. This is the data from the Montgomery textbook, example 14.2, with assembly time, and I have fixture,
You need to share
layout, and
again. You need to
operator.
share one more time.
Okay, did I just get cut off again?
Yeah, you're not sharing. It's not sharing.
Yeah. Okay. Oh, share. Oh, sorry. Share my screen. Yeah. Sorry. Okay. Thank you. I apologize.
John, you're muted right now, it looks like.
Okay.
Yep, we can hear you,
Sorry
but we
for
can't see the
trouble
screen.
here. Okay, so you can hear me, and
We hear you, but we can't see the
you can see
screen.
my screen. and I'm back to the assembly. Okay, let's try that. You are, can you see this? Can you see my screen?
No.
Okay, I'll stop sharing and try it again.
Coming up.
Are you able to see my?
Yes, we see your screen now. We see the Excel file.
Okay, sorry for the trouble. All right, we'll get through this. Okay, so from the top, this is the assembly time data from.
He's having very strong difficulty. John, we can't hear you again. You locked up. Does anyone have any questions while we're waiting?
Okay.
I can answer most of them.
Hang on a second. Why am I getting this?
John, you locked up on us again.
Yeah.
We see your
So
screen now.
you're not able to see my screen?
Yeah, we can see it now.
Okay. And you can hear me?
Yes.
Okay. All right, let's try it again. So this is the assembly time data from Montgomery's textbook, example 14.2, where we have two fixed factors, fixture and layout, and a random factor operator, which is nested within layout. There are different operators within each layout. And we have the assembly times. So what I want to do is I want to analyze this as a hybrid. I'm interested in both variance components as well as the classical ANOVA analysis for the fixed factors. So it's a mixed model. And what I want to do now is I want to run general linear model. And time is my response. I have fixture as a fixed factor, and I have layout as a fixed factor. I have random factors. And
John, you're locked up again on us. Not sure what's going on his end. I think it's on his end. I could see Jeff. Looks like Jeff's moving, so I assume that everything's working good. So does anyone have any questions about the technique that he's using? It's a very valuable technique. As a statistician, I use it all the time for random effects and mixed effect models. John, I just was summarizing. Sorry you locked up again on us. I see you're back.
yeah, I'm
I was
back.
trying to summarize, see if there were any questions on things. And again, this is a technique used a lot by many of us. I use it on many data sets.
Yeah.
So any questions anybody have? I don't know why it was locking up.
Yeah, I'm so sorry, folks. You know what? Let me just try running it again and see if you're able to see my screen.
Yes. No, not yet. We can't see your screen.
Yeah.
You still there, John? He's locked up again. So I think we're going to wrap this up. Don't know what's going on that end. Does anybody have any questions? Again, I use this technique a lot, so I can probably answer many of them. If you have questions, I'm trying to make sure I get attendance. So hang on, don't get off yet. make sure I get everybody's attendance on who's here. So, but do you have any questions? You can put it in chat. I'm gonna freeze, stop the recording here.